Hey everybody, this is the second lecture video for week 2. The first one was about adding vectors and talked about vector components. Let me share the screen. For this one, we're going to now be talking about motion in 2 and 3 dimensions and really the vector nature of position, displacement, and velocity, right? And so we're going to redefine those. We in chapter 2, position and displacement and velocity are really just defined in one direction. But now we have to deal with the vectors of, or the components of the vectors of these quantities. So let's start with position. And I just want to first of all introduce some notation. So when we're talking about position, it really is a vector, right? So for example, let's say I have an object here and my origin is down here. So maybe I'm throwing a ball and the ball is flying through the air. And I would draw a line directly to that. This would be my position vector. And so I'm going to use the notation R with a little arrow above it to denote that it's a vector. Now, in the book, it might be a boldface type that is used too. But this is a vector, so it has an X and a Y component. And if I am using the typical I hat, J hat notation, I would write this as X I hat plus Y J hat. So hopefully now you can see that the X and the Y are really the components of the position vector. Now the position can change. It can move maybe over to here. So I might have a second position. Maybe I have an initial and a final position vector. So I'm going to call those Ri and Rf. Now, before I go on to the next thing here, I do want to point out that we can also talk about 3 dimensions. For this lecture, I'm going to mainly talk about 2 dimensions just to keep things simpler, but it's really straightforward to add a 3rd dimension. And typically for our 3rd dimension, that would be our z direction. So in the diagram I'm showing here, kind of out of the screen or into the screen. And the unit vector that we use for that is k hat. Okay, now position can change, right? So the position can depend on time. So I could write all of this as a function of time. So x could be a function of time. And again, the I hat is just a unit vector denoting the x component, plus y function of time j hat, plus z function of time k hat. So all of these things can be changing, and the vector will be basically an arrow pointing from the origin that moves around and follows the object. So that is the definition of position in 2 or 3 dimensions. So let's talk about displacement now. When we make a displacement, what we mean is we change our position. So in the previous chapter 2, displacement was just written as delta x. Now we're going to be talking about, again, motion in 2 or 3 dimensions. So this is now a vector, and it's going to be delta r, right? And that's going to be delta x I hat plus delta y j hat. Now, just to again, make it simpler, I'm only going to talk in 2 dimensions in this case, but there could also be a delta z k hat on here. But let's just keep it simple for the moment. And again, I want to point out that by delta x, what I mean is x final minus x initial. And by delta y, y final minus y initial. So just to, doing a quick example, let's say that we have an initial position vector of 5, and we'll assume the units are meters, but let's just, to make it simpler, right, keep the units out of it for now. 5 I hat minus 3 j hat. And how about, that'll be our initial vector, and then we're going to move to an R final vector of negative 2 I hat plus 6 j hat. How do I get the displacement? Well, I just subtract the components like I would for any vector. So my displacement vector for this movement from R initial to R final is going to be R final minus I initial, for the x component, it's going to be -2 minus 5. So it's -7 I hat. And then for the y, it's 6 minus -3, which is plus 9 j hat. Now I can get the magnitude and the angle for this vector the same way that I would in the first lecture video, right? Just using some trigonometry. But this would be our displacement vector. Okay, now let's go to velocity. When I talk about velocity, I have to be a little bit careful because for the displacement in the previous slide, I didn't really specify the time, right? And it can be a finite time interval. So it might be a time interval of 1 or 2 seconds that I go from R initial to R final. If I calculate the velocity in that case, I'm going to get what's called the average velocity. So let me just write down the definition. So the average velocity, which I'll call AVG, still a vector, of course, but it's going to be the displacement vector over the change in time, right? And again, this is exactly what you'd have in one dimension. If you were just moving along the x, you would have delta x over delta t. But in 2 dimensions or 3, this is the x component. And we also have a y component. So delta y over delta t j hat. So again, going back to our previous slide, let me just take a look at it again. We had this displacement, -7 I hat plus 9 j hat. So when I write out my average speed, I'd have -7 I hat plus 9 j hat. That's my displacement vector. I'm going to divide that by the time. So let's just say, as an example, it is 2 seconds. So the time interval over which this displacement was made was 2 seconds. I'm going to divide this by 2 seconds, and that would give us our average velocity vector. Okay, now, how do I do algebra or math with vectors? The main thing to keep in mind is that the components of the vector are independent of one another. So I'm just going to divide the 2 into each component. All right, so I'm going to take the -7 over 2. So I'm going to get -3.5 I hat plus 9 divided by 2, which is 4.5 j hat. Now I haven't put the units in at this point, but if my displacement, my positions were in meters, and my time here is in seconds, both of these would have units of meters per second. So I've got a -3.5 meter per second velocity in the x direction, or the x component, and 4.5 meters per second in the y component. Now again, this is an average velocity because over that 2 second interval, I could have moved around a lot. So this is just taking the average velocity, but over that whole 2 second time, from my final position minus my initial. Right? There are a lot of ways to go from that initial to final. So this is my average velocity. Now let's talk about instantaneous velocity. In this case, we're going to look at the situation where the time or the position, r of t is a specific function of time. So let's make one up here. Let's say it's 2t squared I hat, so that will be our x component, minus 3t j hat. So there's our y component. Now the question is, from this, how do I determine the position at any time? Right? Well, I might just plug in whatever time I'm interested in. For example, 1 second would give me a position at a time of 1 second of 2 times 1 squared, which is 2 I hat, and then minus 3 times 1 second minus 3 j hat. All right, so I can see how plugging in any time in those 2 functions gives me the position vector at any time. But then the question is, well, how do I know the velocity at any particular time? Okay, well, we know that the velocity is the derivative of the position. So I just have to take dr dt, but now I'm taking the derivative of a vector. Well, how do I do that? Simple. I simply take 2 derivatives, right? I'll take the derivative of both the x component and the y component separately. And this is what we call our instantaneous velocity v. Now it is still a vector. So when I take the derivative of the x component, I'm going to get 4t I hat minus 3j hat. So I just took the derivative of both of those separately. Now notice the velocity in the y direction, the y component is now a constant after that derivative. Okay. So now I have a function of velocity as a function of time, an instantaneous velocity that I could also plug in the time and determine what that velocity is at any second. Now, again, I need to be careful with units. I've not put them here because just to keep it simple. The other thing I want to point out again, there could be a z component. I may have a third k hat here. Again, I'm just keeping it simple for now. Okay, so that's the definition of position, displacement, and instantaneous velocity in 2 or 3 dimensions. The next lecture, I will talk about acceleration.